Hello everybody, we are Team Cast and we're representing SNK Aminuddin Baki KL. My name is Chua.
My name is Zoyan.
My name is Aidan.
And that's all. Thank you.
Thank you.
Thank you.
In Malaysia, schools face the challenge of a hot and humid climate, which require a constant need for cooling and lighting to keep students comfortable. Unfortunately, the way our current solutions manage energy isn't very efficient, as it often fails to solve real-life needs, resulting in a lot of electricity being wasted during toilet breaks, breaks between classes, or when classes are empty. That's where our ACEMS, Automated Classroom Energy Management System, comes in. We aim to reduce electricity wastage by 50%.
This slide is about the existing solutions that schools in Malaysia currently use to fix the problems stated in the problem statement. First, there is scheduled timers to turn off fans and lights. Although this solution is rarely used in Malaysia, it works by setting a specific time for the fans and lights to turn off, for example, when the school finishes. But the major flaw with this solution is that it doesn't know whether there's any students in the class. For example, if the class goes to the library to study, the fans and light will still be on. Next, moving on to a more common solution, which is turning off lights and fans when not in use. Although this solution is quite effective and common, students might forget to turn off the fans and lights. Next, the second solution, which is changing to energy efficient LED lights and fans, such as those fans and lights that is rated 5 stars in energy saving. Although they can save energy while it's running, it won't save energy if students or teachers forget to close it. The third existing solution is using motion sensors to detect presence of humans. As although this one is a rarely used solution in Malaysia classroom, as it's not used in many schools, I will still be presenting about it in the next slide in more detail. That's all for the existing solution slides. Thank you. This slide will be explaining on the third point of the existing solution, which is using motion sensors. Thus, it will be explaining on the weakness of the motion sensor and comparing it to the ACEMS sensor, which is the VL53LX distance measurements sensor. So I'll be comparing using 4 capabilities, which is stillness detection, environment interference, field of view, and IoT integration. So moving on to the first capabilities, which is stillness detection. The motion sensor will fail as the student is not moving, especially when they are sitting at the desk studying. While the ACAM sensor, which is a distance measuring sensor, is precise as it is code to measure the specific distance to know whether there's a human there or there isn't. Next, there is environment interference. The motion sensor is easily influenced by its environment, while the ACAM sensor is not influenced at all as it only measures the person at the desk. Next, there is field of view. As I said earlier, the motion sensor is highly interfered by its environment, and here in field of view it has a very wide field, as it can be triggered by the motion of others walking by, while the ACAM sensor only measures the person sitting at the desk, hence it is specific and it won't be interfered. Lastly, there's the IoT integration. While the motion sensor has none, the ACEMS sensors can wisely update the school about energy usage, and also the school is able to change the settings of this solution wisely without requiring hardware maintenance. Through this is because we use a Raspberry Pi Pico W, which means it can connect through Wi-Fi. That's all for me. Thank you. So welcome back everybody. This is the physical version of our project, which is ACEMS, which stands for Automated Classroom Energy Management System. And as if you've seen the slides, it is on the first page. So moving on, a quick disclaimer that this project is a non-working one. So I'll just be explaining the function of the parts and also all the main components. So the main components are, first, the VL53LX distance sensor to measure the distance, and here is the Raspberry Pi Pico, Raspberry Pi Pico W, which is the microcontroller for this project. And lastly, there's the relay module, which acts as a switch to cut the electricity when this system detects that there's no people. So I'll first explain the function for the VL53LX distance sensor. So this sensor shoots a 940 nm infrared light pulses at the person sitting at the desk, or either at the floor if there's nobody there, and sends the information to the Raspberry Pi Pico W. So moving on, there's the Raspberry Pi Pico W, which is connected by all these wires leading to the Raspberry Pi Pico W. The Raspberry Pi Pico W takes the distance data from the sensor and determines if there's a person there or there isn't. So, and it will tell the relay module, which is this one, to whether to turn off the light or the ceiling fan. So moving on to the function of the relay module. The relay module acts as a switch to cut off the electricity of the lights or the fan or the ceiling fan. So now I'll be explaining the methodology for this whole project. So I'll start off first with the VL53LX time of flight sensor. So this sensor will work by releasing the light pulses that I've mentioned earlier in the component specifications and their functions. So it will be released every 60 milliseconds, which is equivalent to 1 time per second, and it will measure. So its job is to measure the distance between the human or the floor from it to determine whether there's a human sitting at the desk or there isn't. Next, it will send the data to the Raspberry Pi Pico here. The Raspberry Pi Pico will contain the code which will determine whether to tell the relay module to turn off or on the lights or ceiling fan. So the codes will instruct it to. Thus, the code will contain a specific measurements for the measurements that is received or calculated by the sensor. So the measurements are 0 to 15 cm, it will instruct the relay module to turn off the ceiling fan or the lights. And if 20 to 55 cm, it will instruct the relay module to turn on the ceiling fan or the lights. And if it's 60 cm and above, it will instruct the relay module to turn off the ceiling fan and the ceiling lights. And prevent the ceiling lights or ceiling fans from turning off while the person is sitting there, we will set a special settings also to, if it detects slight differences of 0 to 10 millimeters while measuring the distance, it will tell the relay module to avoid cutting the electricity. Lastly, there will be the relay module. It will cut off the electricity of the fan or light based on the input received from the Raspberry Pi Pico W. So that's all for the explanation on the prototype. Now I will be presenting how my team planned for the solution to be implemented in a real classroom. First, there will be the VL53LX sensor. It will be placed just underneath the wooden part of the top part of the table, as you can see in the slide. It will be covered in a box to prevent damage from the students, and also it's hidden underneath at this spot to prevent the students from knocking it over. Next, the wires will be all covered with PVC trunking to prevent messiness and danger to the students. Moving on, there will be the Raspberry Pi Pico W, which also will be covered in a box, but it isn't shown in this. The box isn't shown in this slide to prevent to to show the Raspberry Pi Pico W. Next, moving on, inside the electrical switch, which is covered to prevent electrocution, there will be the relay module, which will cut the electricity off when it detects when there's no one there. Moving on, my team members and me will present a deeper explanation on the components and also the prototype, so to understand it better. Thank you.
Hello everyone, my name is Adam and I will be explaining the software architecture based on our project. Starting with our core system parameters, we have structured the firmware to be modular. We have configured GP4 and GP5 on the Raspberry Pi Pico W to handle the I2C serial data and clock channels for our laser sensor, while GP0 acts as our digital output line to control the relay module. Most importantly, we've hard-coded our detection thresholds into centimeters. The active user zone is strictly defined between 20 and 55 centimeters. To accommodate traditional states and sensor noise, we've purposely engineered an uncertain zone buffer between 16 to 19 and 56 to 59 centimeters to ensure our automated relay doesn't rapidly toggle due to minor physical shifting. Moving on, we developed the read distance CM helper function. The VL53L0 at time of flight sensor natively communicates its distance measurements in millimeters. Our script utilizes division to convert those raw values directly into centimeters for easier categorization. Furthermore, this is wrapped in a fail-safe try except block. If a hardware read error or communication lag occurs, if either of those occurs, the function gracefully returns a value of -1, preventing the entire project system from crashing in a real, let's say, a classroom deployment. Once a valid distance is captured, it passes directly into our core evaluation, which is also known as the classified distance function. This function uses a conditional framework to instantly label the data into one of the three operational states. If the distance falls within our user parameters, it returns an occupied flag. If the target is closer than 50 centimeters or farther than 60 centimeters, it triggers an empty flag. If it hits our buffer gaps, it marks the status as uncertain, instructing the system to preserve its current state without making sudden modifications. Finally, everything comes together in our execution loop, which samples the classroom environment precisely every 1 second. When the status is occupied, the system immediately resets our tracking timer to 0 and commands the relay pin high, powering the appliances. However, when the status switches to empty, an internal counter begins accumulating seconds. Rather than turning everything off instantly, which would disturb the class if a student simply stepped away for a brief moment, the system tracks consecutive empty ticks. As soon as the counter cross references and matches our 180-second timeout configuration, the system verifies a long term vacancy and commands the relay to pull low, safely cutting power to the fan and lighting fixtures to optimize energy conservation.
Lastly, the benefits of our solution is that it saves more electricity, it is more precise compared to normal motion sensors, and it has wireless data report IoT, which stands for Internet of Things, which means the school can wirelessly update the system if change is needed, and the school can receive wireless update on electricity from the system.